This is a system level overview of our hardware for the lock monitoring technology. We will start with the microchip microcontroller, the Atmega 32U4. That's connected to 4 different peripherals in this system to accomplish the goal of monitoring a door for basically whatever you would want to know surrounding the door, whether or not it's closed, whether or not it's locked, and whether or not someone is around it, someone's moving around it. And respectively, the sensor that we use for detecting whether or not the door is closed is this infrared sensor right here. So in the frame of the door, we have a pulsing infrared LED that will only be detected by this sensor if they're directly in line, as in if the door is closed. Moving on to the motion sensing technology, we use this low-cost radar module. It operates at a frequency of 3.2 gigahertz, and it has a range of about 6 to 7 meters, where it'll function on the principle of it sends out this pulse, and then if anything with water in it, basically, such as a person or an animal, is moving either towards or away from it in its radius, then the received pulse will be either shorter or longer, and that change can be detected. So that will take care of most of that work and simply tell the microcontroller whether or not something's moving. That leaves our last sensor, the BF350 pressure sensor, which we use for whether or not the door is locked. So in pretty much all mechanical doorknobs, the lock function will slide a metal plate back and forth internally to the lock. So we've placed this pressure sensor at that metal plate to know which position it's in. And then to process that data, because the change in the pressure is relatively small, to process that data, we use a load cell amplifier integrated circuit. And that board conveniently outputs the data 10 times per second to this microcontroller right here. Then once we compile all of that sensor data, we process it locally on the 32U4, and based on the pressure, the presence of infrared light, and the presence of motion, we can generate a report that we send over UART to our LoRa network. That's conveyed in several different status codes that we've made to reduce the amount of traffic that we generate on the network. We've been able to reduce that to a single byte that we have to send.
This is our software structure for the project, and for the first when our LoRa send the data to the SANET, which is our LoRa platform, and it will send connected to the SYNSpeak. Why we need SYNSpeak? Because SYNSpeak have a HTTP protocol we can use to generate the JSON object. And when we got the JSON object, the data will transmit it to the 2 main components. The first part is our web application. And for the web application, we use GitHub for the version control, and we also host this on the GitHub so that we can update the website all the time. And for the implementation, we implement both client side and server side for the web application. We directly use the fetch function to fetch the data into the web application, and also use API leaflet.js to map the real-time location for our data. And for the Android app, we use a library called Volley. It just connected directly to the JSON object, and you can get the real-time status of the data with one simple click. For the Google Assistant, it uses a platform called Dialogflow, which is a natural language processing platform. And in the Dialogflow, you can implement your own microservices under their webhook so that you can implement whatever you want.
Hey Google, talk to Smart Lock. Here's the test version of Smart Lock.
Good day. What can I do for you today?
Show me the status of my lock.
Pressure sensor active. IR sensor active. Motion sensor active. Your door is open, locked and motion detected.